All right, so we're going to continue looking at a couple of more related rates problems. So the first one is, it says a man is walking at a rate of 5 feet per second towards a street light that's 20 feet high. The man is 6 feet tall. We want to determine how fast the length of his shadow is changing when he's 24 feet away. And then we also want to look at how fast the tip of his shadow is moving, which may essentially kind of seem like the same question, but in reality is actually a little bit different. So let's start by looking at an applet. So let's take a look at this one. So this is not our exact scenario, but it's pretty similar. So here we have a boy on a skateboard, and he's going away from although I can move him back towards it. So he's moving away at a constant speed, and we're looking for, again, how fast is his shadow increasing in length. So ours will be the opposite. It'll actually be a shadow that is decreasing in length because he is going towards the light in our example. But let's just kind of take a look at, let's get him back starting at the light. He's going away from the light. So in this one I have to kind of pull, again, I'm trying to pull this out at a constant rate. So he's going to be moving out at a rate of 3 feet per second. And if you can focus on the shadow length, you can see that dark line from point B to D is getting larger, and we want to know how fast is it getting larger at a particular instant. So for us, he's actually walking back towards the light at a speed of, in ours I think it was 5 feet per second. So let's bring him back towards the light. Again, I'll try to do this at a constant speed with my finger, and you want to look, although it wasn't there, but you want to look at how fast, in this case, is his shadow getting smaller. And then you also want to look at the tip of his shadow. So the very tip, looking at point D. And so as you look at point D itself, point D is being affected by two things, both how fast the length of his shadow is increasing, but then also how fast he's actually moving to the right. So I think I can do this if I'm not going so slow, I can do it more fluid. So as I just kind of slide to the right, notice that the shadow kind of looks like it's increasing and decreasing in a constant way. Do you kind of see that? The shadow length, that bold line from B to D, that shadow length looks like it's increasing or decreasing at a constant speed, but that point D, it doesn't. So if we look at just focusing on the point D itself, as I move further off to the right, it seems to move quicker than when I am, closer here to the left. So I don't know, we'll take a look at this and kind of see what we come up with our calculus. All right, so let's go back and take a peek at what we got here. So let's attempt to draw that situation that we had there, which was really similar right triangles, one sort of drawn inside of the other one. So we've already seen a pretty decent picture of what we have here. So I'm just going to attempt, in my best of somewhat limited drawing capabilities here. So what we had was, so let's say this is my man right here. So this is the man that is 6 feet tall. And so obviously, when you think about, this person here, his height isn't changing at all. So we can leave this height right here. This is a constant 6, so that's why I'm putting it on the picture. The other thing that is constant, so up here is my light. So this is my, wow, beautiful artwork. Gorgeous. Okay, so there is my street lamp, and that street lamp height is also not changing. So this height is 20, so that height is not changing. And what we have are two right triangles where they both have a right angle in the lower left-hand corner, and they both share the same lower right-hand corner angle. And since the angles of a triangle have to add up to 180, that means their upper left-hand corner angles are equal, And when all of the angles are equal, you have what we call similar triangles, so their side lengths are proportional. Okay, so let's label these quantities that are changing. In our situation, he is walking towards the light, so this is changing. His shadow length here is also changing. So we have the length of his shadow that is also changing. So these are kind of two different quantities. So we're going to label them with different variables, A and B. All right, so let's see what we have. We're told that he is walking towards the light, so that's how fast he's moving in the A variable, how fast A is changing with respect to time. Now on this one, what we have to be a little careful about here, so yes, he's walking at a rate of 5 feet per second, and yes, that's going to be my dA dt here. But because A is getting smaller, so let's highlight that, that's going to mean that we have to label this with a negative. So that speed is negative 5 feet per second. All right, so that's the dA dt. And then we are looking for how fast the length of his shadow is changing. So we want to find the dB dt. So we are initially here looking for the rate of change. Oops. The rate of change of the length of his shadow. So we want to find dB dt. And we want to know that at the instant when he is 24 feet away from the base of the lamppost. So when A is equal to 24. All right. So what we want to do this time is set up our equation is going to be based on proportional side lengths of similar triangles. So the manner in which you set this up doesn't matter when you set up a proportion as long as you're consistent on with each ratio. So for example, let's suppose I am setting up my ratio as a base to height ratio. So as long as I'm consistent with that, then it doesn't matter. I could have done height to base or something like that. So let's start with our smaller right triangle. So base to height ratio on my smaller right triangle here is b over 6. And then be careful, this often gets students, sometimes they're real quick and they go, oh yeah, b over 6 is proportional to a over 20, right? Wrong, right? You need the full base. The base of the bigger triangle isn't just a, it's a plus b. So be careful about that. Now, while you are certainly within your rights, I guess I'll say, it's certainly fine to go ahead and differentiate with respect to time. I would probably clear the denominators and do a little bit of simplifying first. It's just going to make, I think, the derivative process and such a little bit easier. So first we could maybe write this as 20b is equal to 6 times the quantity of a plus b. We could also do just a little bit of reducing here if we were to just kind of think about, I don't know, dividing both sides here by 2. So we would have our 10b is equal to 3 times the quantity of a plus b. And then if I distributed on the right there, I'd have 3a plus 3b. And then I could get all of my b terms together on one side. So I could subtract the 3b. And so this is still just the original relationship that started off with that proportion. So 7b is equal to 3a. That looks a whole lot nicer in terms of differentiating. So that's what we're going to do next. So we are going to differentiate both sides here with respect to time. And again, you could have done it in the first one. It just would have looked a little uglier, right? All right, so following our rules for implicit differentiation, when I differentiate a b term, I have a 7 there, and I multiply by my dB dt. And on the right-hand side, when I take my derivative, which is 3, I multiply by my dA dt. All right, so what am I trying to find in this one? Well, I'm trying to find dB dt, of course. So let's just go ahead and, divide both sides by 7, and then we'll sub in our dA dt. So it looks like we end up with here how fast the length of his shadow is changing, dB dt, looks to be 3/7 times, and that dA dt we know is -5. And so that now means the length of his shadow, I hate it when I do that, the length of his shadow is changing at a rate of -15/7, or what's that, -2 1/7. And this would be, the B is measured in feet per time is measured in seconds, so feet per second. So this is giving us how fast the length of his shadow is changing. So this is the rate of change of the length of his shadow. The negative makes sense because that length is also getting smaller as he goes towards the light. The length of his shadow is decreasing, so getting that negative makes sense. Now, how fast the tip of his shadow is moving. So now the second question is about the rate of change of the tip of his shadow. So, just a second here. So the tip of his shadow. So before we get into that, I also want to just kind of point out one other thing here. Did you notice that we never needed to sub in that A equals 24? So if we kind of went back and looked at the picture, that was really revealing that the rate at which his shadow was decreasing, just focusing on the shadow length, it was constant no matter what time or location, I guess we'll say how far he was either away from, or if he was moving towards or away from the light. So the length of his shadow was changing at a constant rate. So the sub in A equals 24, sub in A equals 10, it was always the same rate of change of the length of his shadow. All right, now we want to focus on the rate of change of the tip of his shadow. So the tip of his shadow is impacted by two things. It's impacted by how fast he's actually moving towards the light, and it's impacted by how fast his shadow was decreasing. So the actual tip of his shadow, so this point right here, let's say, so the rate of change of the tip of his shadow is going to be how fast he's moving to the left. So even if the shadow length stayed the same for some reason, if his shadow length were to stay the same, then it would still be moving as he's moving towards the light. But also the length of his shadow is actually changing. So in this situation, both of those kind of like adding up, these two rates, gives us that the rate of change of the tip of his shadow is -7 1/7 feet per second. Okay, so actually, that is also going to be a constant speed at which that's changing. At first, when I was looking at the applet, it kind of looked like the tip was changing. It was definitely moving more quickly, but I was having a hard time dragging that at a constant rate. So the tip was moving more quickly, but still at a constant rate. All right, so let's look at one more example here. It says the patrol car, I'll get it yet. A patrol car is parked 50 feet from a warehouse. There's a revolving light on the top of the car. It's turning at 30 revolutions per minute. And we want to know how fast the light beam is moving along the wall when it's at an angle of 30 degrees. So you guessed it, let's take a look at an applet. These can be really helpful in getting a good visualization here. So let's look at a similar one. I like this one because it's already animated for me. So this one's a super similar situation, but instead of a car parked away from a wall, we have a lighthouse that is specifically 3 kilometers east of the shore. So a lighthouse and the shore versus a car and a warehouse. This time the light is rotating at a constant rate, 4 times per minute. Ours is rotating at a constant rate of 30 revolutions per minute. This one is 4 revolutions per minute. Makes sense, right? A lighthouse would go a lot slower than a revolving light on a cop car. And we want to know how fast it is traveling along the wall at a particular instant. In this example, it's when it is 1 kilometer north. In ours, it's going to be when the angle is 30 degrees. So we'll have a slightly, but it's still, now watch the light move along the wall. Now, that's when they wanted to know. So we have a very similar kind of situation here. But we want to know at the instant when the angle is 30 degrees. So let's go ahead and go back and see what we can come up with here. Now, a lot of times you may be given a picture with some of these. And all of these we've kind of started, it was supposed to be a horizontal line. I'm bad about remembering that I have this lovely little ruler feature I can use here, and I often forget it. So let's say that that's, I don't know, our warehouse, I guess. And then we have our cop car that's going to be a certain ways away here. And let's draw in an angle. All right, so let's take a look at this. Okay, so suppose we have, let's let this be, I guess, our warehouse wall here. And I guess the way I have this one drawn, we're going to let this be our cop car. The art is outstanding, is it not? And this can be labeled the 50 feet that it is parked away is not changing. So I would put that on my picture. What is changing is going to be this angle theta that we're going to be interested in, as well as then how fast the light is moving along this warehouse wall. And so let's give that a length of x. So I'll call that x over there. All right, so here's what we have. Now, other information we are given. We are given information this time about the angular speed, how fast theta is changing with respect to time. So we are told that theta, the revolving light at the top of the car, turns at a rate of 30 revolutions per minute. Now, what we need to be careful about here is everything we do that is related to angles or trig is not based on revolutions per minute, and it's not based on degrees per minute. Everything that we do with trig is going to be based on radians. So, I mean, really important. I mean, think about some of our even early proofs of like the limit of sine x over x. We start with arc length, and the definition of arc length that we use is based on radian measure. So everything's always based on radians. All right, so we need to get this into radians. So what we want to think about then, of course, is that there are angular 2 pi radians that is equal to 1 full revolution. So we have a little dimensional analysis here that will get us out of revolutions and into radians. And so I'm going to go ahead and leave it like that. If they had specified that my label needed to be in, let's say, how fast is the light moving in feet per second, then you could make the choice to either make that conversion here as well and convert the minutes, 60 seconds in 1 minute, so you could divide by 60, or you could do that at the end if it's specified. So here I think we're okay though. We have 60 pi, and then just kind of being mindful, this is now in radian measure like we wanted per minute. So that would just, again, be something to be mindful of depending on if they had a specified unit that they wanted in their final answer. All right, now what do we want? We want to know how fast the light beam is moving along the wall. So that is the dx dt. So we want to know that dx dt, and we want to know that, so how fast is the light beam moving along the wall? And we want to determine that at the instant when theta is equal to 30 degrees, or I'm just going to go ahead and write that as pi over 6. When you're subbing it in, it probably won't be that big of a deal. You can mentally think of it as 30 degrees, but let's just stick with radians. That's what I got done saying. Okay, so sometimes students' first instincts are like, hey, right triangle, Pythagorean theorem. But Pythagorean theorem has nothing to do with angles, and we have an angular speed here. So as soon as it has information given to you about angles, or you're looking for something about angles, you need to think about the trig ratios. And look at that angle theta, and look at the two sides. It's not the hypotenuse, it's the x and the 50. So we have opposite sides and adjacent sides. So the trig ratio that you should be thinking about should be either tangent theta equals x over 50, or you could think about cotangent of theta equals 50 over x. And there will be times that you'll want to use this one. I would pick, obviously, the tangent one, not because it's tangents. So I would, go with the form that is the x over 50, because that's going to be easier to take. If I think of that as 1/50th x, that is going to be easier to take its derivative. So if that had been the cotangent one, I'm going to go with that one. Happens to be tangent here, but I'm going to do that because it would be an easier derivative. Right, so just kind of be thinking about that. That could come up in the other direction, and maybe cotan would have been the better choice. All right, let's dig in here, and now we're ready to take our derivative with respect to time, of course, of both sides. And so we're going to take our derivative of tangent of theta equals, and then the derivative of 1/50th x there. All right, so the derivative of tangent is going to be our secant squared of theta. We just differentiated a theta, so we're going to multiply by d theta dt. Derivative of 1/50th x is just 1/50th. That's kind of why we went with this one. And then dx dt. Okay, so we are trying to solve for dx dt. Again, you kind of have your choice in what you would prefer to do, either solve for it first or solve for it later by subbing in the numbers first. Let's go ahead. Again, I think more conventionally, homework and stuff might show it as isolating for dx dt first. Now, something that I would say to be mindful of here, it might make your work a little bit easier, is that secant squared is really the same thing as 1 over cosine squared, right? And if I'm going to have to solve for and kind of get that trig function on the other side, it might be easier to think of it as the 1 over cosine squared and then just multiply both sides instead of dividing by secant squared, which you could. It might be easier to show it as multiplying by cosine squared. Or when you get to the point on the right-hand side, maybe just thinking of 1 divided by secant squared would equal cosine squared. What am I doing? I am supposed to be back this all up. I'm supposed to be isolating for dx dt. I'm so sorry. Well, let's still think of this as 1 over cosine squared. We just need to isolate for dx dt. In my head for a second, I had us isolating for d theta dt. It's been a long day. I've been recording quite a few videos today, and it's after 5 o'clock, and I need to pack this in. Last one. So let's go ahead and multiply by 50. All right, so now thinking of it as 1 over cosine squared, though, will be useful as we get ready here to sub in some given quantities. All right, so we have our dx dt here is equal to. All right, so we have our 50, now our 1 over the cosine squared. So we have our, what angle are we subbing in here? Oh yeah, pi over 6. So we're going to have our 50 times 1 over the cosine of pi over 6 quantity squared, and then our d theta dt, so that's the one we had to convert into radian measure, and so that was our, gosh, what was it? 60 pi. I'm losing it today. 60 pi. Okay, so now your cosine at pi over 6. So your x-coordinate there at pi over 6, so that's like your root 3 over 2. So this is like root 3 over 2 quantity squared. And so that would be like 3/4. And that's all in the denominator. So 1 divided by 3/4 is going to be like multiplying by 4/3. And then times our 60 pi. And that is all equal to our dx dt. So doing some reducing there, 60 divided by 3 would be our 20. Our 20 times the 50, so what, 1,000 times 4. So this should be 4,000 pi. And so this is our final result here for dx dt. Or if you want, I didn't, 4,000, hold on. Pi. So if you wanted, or if they asked you to go to decimals, this would be like 12,566.37. And so this is how fast the x was labeled in feet, and then per. The t here was actually in minutes. So this one would have been feet per minute. And so this would be our final answer. All right, so that's our dx dt that we were looking for there. And then if they wanted you to convert into feet per second, you could multiply by your 60 seconds there. Divide by your 60 seconds. So if you wanted to take that and divide by 60, this would have been approximately, so we could divide by 60 if they wanted this. So I'll say, or that came out to be, I just did that quick in my calculator, 209.44 approximately, if they specified in feet per second. So that would have been another option there. All right, so that's our last related rates problem for this section. You can always do more from the homework. There's lots of different really interesting types, so we can always do those in our Zoom sessions.